Hello everybody. Welcome to the first virtual lecture that I'm giving on unsupervised clustering. Today we're going to be talking about some methods that you can use to analyze a dataset that doesn't have any labels associated with it. So all the methods that we've worked on so far have focused on datasets wherein you have some feature data as well as some labels. And we're going to use unsupervised clustering to deal with the situation when you don't have labels for any one of a number of reasons. So just to recap, in case you forgot about some of the stuff since the break, we consider our training set to be a limited random sampling of the feature space, and we consider that there's an infinite number of possible features that we could be collecting from the world. And so the training set that we observe is a limited random sampling of that feature space. In supervised learning, we have feature vectors, which we denote by X, and we have associated class labels, which we denote by Y. And so Y here is an element of the set of possible class labels that we have associated with this sample. And this is what we've been using so far to train our data sets. In unsupervised learning, we have a set of data that is essentially not associated with any class labels. So we have feature vectors, we have a number of feature vectors that make up our training set, but we have no class labels for that data. We've seen a lot of different approaches to classification using these class labels as an indication to build a model to predict the class of future samples. So in Bayesian statistics, we use our dataset to predict the probability of observing a particular class given that we've measured its feature. For decision trees, we split our dataset using optimal feature thresholds. These are the branching points, and we discussed various ways that you could select optimal feature thresholds as you build your tree. In linear discriminants, we build a set of functions, which we denote by G. And this set of functions, we have one of these functions for each class that we're interested in. And the predicted label is omega sub j, where j is the associated index of the largest discriminant function. So if you have three classes, you have three discriminant functions, given a feature vector, the value of the label that you assign to that feature vector is the discriminant function that gives you the best or the highest value. So you could select G to be essentially your probability or the inverse of your risk and so forth. In K nearest neighbor, you don't do any sort of modeling, you don't do any sort of parameterization. You essentially say, I'm going to look at the K nearest neighbors for each sample, and I'm going to assign the sample vector X, which I measure, to the class associated with the K nearest neighbors, or the most common class among the K nearest neighbors. If we use one of the methods that we've talked about before that deals with a model, that model is parameterized or defined by a set of parameters. And typically we've been assuming that most of our features come from a normal or a Gaussian distribution. And as we've talked about several times, the normal distribution is parameterized by a mean and a variance or covariance. But there are lots of different possible distributions that you could use to define your data set and to model your data. Some of them have more parameters and some of them have fewer parameters than the normal distribution. But for the most part, we basically consider the normal distribution to be the most likely. Here's an example of a feature that we've been working with. This is radius mean for our breast cancer data set. And as you can see, we've got both benign samples and we've got malignant samples in our data set. And we collect a bunch of training data, we label them, we assign them to one of these two histograms. Now, we can see here that, for example, a radius mean value between 12 and 13, 81 of the samples in our training set belong to the benign class who have this particular feature value, and only 6 samples belong to the malignant class. And so if we get a new sample that comes in and we measure the radius mean, and the radius mean is between 12 and 13, we can assume that the most likely class for that sample is the benign class. Now in Bayesian statistics, we would essentially take these histograms, we would calculate the arithmetic mean and the variance for each class, and we would create a Gaussian distribution centered on the mean and with the measured variance. And we would use that to model the benign class, and then we would do the same thing for the malignant class. So we would look at the average feature value and the variance of the feature values for the malignant class, and we build two different distributions like so. Now again, there's lots of different distributions to choose from. Each of them has a different form. You may have some a priori understanding of the feature distribution that may lead you to one type of distribution over the other. But generally, you want to choose distributions that describe your data well, so they match the data set that you've collected and that you've visualized. They have relatively few parameters. You don't want to have a large model if you can help it. And they should make intuitive sense. So if your feature values are more likely to be above the mean than below it, then you want to pick a distribution that adheres to that rule. But for the most part, if you don't have any intuition about the type of model to use, you just pick the Gaussian distribution and go with that. It's most often going to be correct, it's simple, it's straightforward, and most of the methods that we've been discussing assume a Gaussian distribution. In the case where you don't want to build a model, then we have a set of non-parametric methods, which we talked about last time. So what if, for example, we don't know what the parametric form of our data set should be? So we don't know that it should be Gaussian. Maybe we have reason to believe it could be something else. What if our samples don't come from a single distribution? Maybe they come from several possible distributions. What if we have too few samples to even create a histogram and be confident in our histogram? And we talked a couple lectures ago about how to estimate the certainty of your mean estimate and your standard deviation estimate. Right? In these cases, we basically can look to non-parametric methods for doing things like density estimation and classification. And we talked about two specific ways of doing this. One is called Parson windows, which is on the top, and on the bottom we have k nearest neighbors. Parson windows you could basically think of as building a histogram, and the main parameter there is the width of the window that you use to characterize your density. And k nearest neighbors, the parameter there is how many neighbors you want to look at to define the region of space that you assign to each bin. Right? Both of these can be thought of as different histogram methods for estimating the density at a particular location. In Parson windows, we can look at the width of the window in the sample space. So this gives you an idea of the bin size that we're going to be working with. And what this does, what these figures illustrate, is that two samples, for them to be assigned to different bins or different parts of the density, have to be far enough away that this detection function will only pick up one sample at a time. Right? So if you have two samples that are close to one another in this space, and if you have a sample that lies here and a sample that lies here, then this detection function is going to assume that they're part of the same sample. Whereas over here, if you have one sample here and one sample over here, this detection function is going to spike at this sample and then go down and then spike again at this sample. Okay? So you can think about this as bin size when you're building a histogram, and you can assume that if you have a large a large bin size like this, then you're going to get a lot of points that are grouped together in part of the density space. Here's an example of the sample space. So this, again, is the probability of observing particular feature values. So this is the probability of x. This is a two-dimensional feature space. And this is how that feature space is characterized using a large window size or a large detection function. You can see that over here we basically get one hill or one mountain that defines the density at this location. Over here, when we use an intermediate size detection function, we see, or Parson window, we see one bump here and one bump here. And then if we use a really small one, which is tantamount to using a very tiny bin size, you end up with three distinct peaks. Right. Now it's up to you and your understanding of your data set to figure out which of these three is correct. All of them are basically different ways of trying to understand the density of the feature space at that location. You can use this for classification by essentially carving up the space associated with each of your different classes and defining your decision function based on these parson windows. And just like we saw previously, if you use a small bin size, right, you could end up overtraining because you end up saying, for example, that this region of the feature space belongs to the black class, where everything around it belongs to the red class. This is probably not an accurate description of what the feature space should look like. It could be that this sample here is an outlier, or it could be that your x2 and x1, which are basically the features that you use to define this sample, are not appropriate for this particular problem. On the other hand, if you use a large H, then you end up undertraining. You end up with a very broad brush that sort of defines big areas of the feature space as belonging to one class versus the other. One thing I want to point out, both of these diagrams have the same samples, the same classes, very different decision spaces, and you can see here that there's big regions of space where you don't have any samples that you've detected. Right? It's very likely that if you sample these parts of the feature space and you collect more data, you may get a very different representation of your decision space. Okay? So, in k nearest neighbor, we basically skip the idea of density altogether, and we say, here are my two features, x1 and x2. Here is a sample that I'm interested in classifying, represented by this x. And so we pick a number of features in this case, or a number of neighbors. In this case, we pick 5 neighbors, and we calculate the 5 nearest neighbors to x, and we assign x to the class that is most common within the 5 neighbors. So in this case, x would be assigned to this class. And what you can see about this is that if you have a sample, let's say right here, right, the choice of your k, or the number of neighbors that you select, could have a big impact on the closest neighbors. And also, depending on where in the feature space you are, the distance it takes to find the 5 nearest neighbors could be very large. Okay, so in this case, you might have to travel pretty far to get all 5 neighbors, whereas if you're over here, you only have to travel a very small space. So the overall density of the space actually does affect the distance it takes, and you may be more certain about this classification than you are about this classification. Right? Again, this is up to you and how you want to define your problem. Okay, but this is what we would consider to be non-parametric methods. And again, just like with parson windows, you can carve up your feature space. You could define your decision space based on the nearest neighbors. This is called a Voronoi tessellation of the feature space. And it basically says that each one of these training samples defines a region around it, and the midpoint between this sample and another sample is sort of defined as the hyperplane between those two samples. When you basically merge the regions for each class, you end up with this sort of decision space. And here, just like parson windows, if you have a bigger number of neighbors that you're looking at, you're going to have a different space that you carve out for your samples. And on the right here, we have the same exact thing, except we're illustrating it in 3 dimensions. Again, just like with all the methods that we work on, it doesn't really matter the dimensionality of the space. The math doesn't care how big the space is. So we can do that. Okay, so now we're going to move on to clustering, and we're going to look at mixture densities. So we're going to look at the case where we don't know what class our training samples come from, and we're going to try and define the densities that are associated with it. So in almost all situations, gathering class labels is hard for any sort of machine learning problem, whether it's biomedicine or natural image collection. Gathering class labels is hard for a large number of samples. we're often presented in the case where data can be collected easily, but they're unlabeled samples. And this is often the case when you deal with large data sets of things like photographs, right? So photographs, there's a number of places where those photographs are collected and harvested, and they could be mined for important patterns, but it's very difficult in some cases to get annotations of what's in each photograph. Telephone audio, or any kind of audio, figuring out what the class is. This is a very common problem that goes back a long way for call centers, where customers would call into a call center and the job of the machine learning algorithm would be to figure out which department to route the call to based on what the person was saying. And this is a very tough problem, and collecting labels for this audio means that a human being needs to listen to the call and figure out what department it's supposed to go to. And that can take a long time if people are long-winded. We also have recorded video segments. So security footage, video game footage, security, is very interested in collecting data and using the image data collected from these videos to detect different types of activities, to find different people or cars and so forth. And so it's easy to collect a lot of video. We have security cameras that are running 24 hours a day. But getting someone to sit and watch the video for things like shoplifters or other criminals could take a long time and could require some amount of expertise. So for some of these kinds of problems, you can actually crowdsource this, and there are platforms out there that you could sign up and actually crowdsource some of your data sets. And if you're dealing in a case where you're building a very simple classifier, trying to detect the difference between cats and dogs, you can essentially ask anyone off the street to classify these pictures. Does this picture have a cat or a dog? And humans are very good pattern classifiers. You could tell, even though the cat is in disguise and the dog is driving a car, humans can still tell that that's a cat and that that's a dog. And that provides a very robust training set for an algorithm that's going to try and classify these images. But when you get to specialized data sets like pathology, medical imaging, cytology images like the ones that we've been working with, the labeling here becomes much more expensive. And so you need trained experts to be able to tell you the difference between a benign and a malignant case. And in some cases, you even need further specialists to tell you how aggressive or what type of treatment to give to the patients who have images like on the right versus those that are on the left. So it's very difficult to crowdsource labels for this type of data. So let's say that you don't have labels, so then what can you learn about the categories that you're dealing with? Well, you can cluster the data, and then you can perform hands-on labeling. In other words, you can get a set of data, you could see if there are any natural patterns or divisions in the data set, and then you can go in and pull a few samples from each cluster and say what each cluster corresponds to. And hopefully that generalizes to the rest of the cluster. You can essentially use this to get an unbiased look at the structure of your feature space. This is really useful in cases where you're not sure how many classes are in your data set. So as an example, let's say that you were trying to train a system to recognize different categories of disease. Well, maybe the data that you have actually represents several different types of disease, but you just think that there's 2 or 3. This kind of analysis will allow you to see, well, are there clumps of data that maybe we're not accounting for in our class space? And this will allow you to sort of design a classifier that can sort of parse out those details a little bit more readily. And finally, you can perform weak supervised classification or semi-supervised learning. This is a pretty important topic. There's been a lot of research on this in the last couple of years. I'm not going to go too much into detail here because it's a bit of an advanced topic. But essentially, the idea behind this is that you can sort of use differently labeled samples to try and build up a labeled training set. There's actually a nice paper out there called A Brief Introduction to Weakly Supervised Learning that goes through 3 different types. The first type of weak supervision is incomplete supervision, where only a small subset of the available data set is labeled. So then you can generalize some of the labels in your data set to other unlabeled samples, and you could use that to increase the size of your training set. You can have inexact supervision where only course level annotations are provided. So for example, if you were trying to determine whether, if you were trying to segment tumor in an image, you might only have a label for the entire image and say, yeah, there's tumor in there, but I'm not going to tell you where it is. That's much faster to label, but obviously it's inexact. And so there are methods that will take that inexact or course level annotation and apply it to a more detailed problem like segmentation. And finally, there are cases where supervision is inaccurate. In other words, labels may be incorrectly assigned. You still can generate some methods that will allow you to do this kind of classification. It's a little bit trickier. You need a lot of these labels. And the assumption is that even if you have untrained lay people annotating these samples, you can still generate a training set that's usable just by collecting a lot of that training data. So, as always, we start with some basic assumptions about our data set, and we move out from those basic assumptions. So, we're going to assume when we do our classification or our clustering that we know the number of classes that we're dealing with, and we're going to call that number C. We're going to assume that we know the priors of our data set, so the prior probability of observing each class. We're going to assume that we know the class conditional probability or density, not necessarily the parameters, but we know what form the parameters are going to be, and in this case we're going to assume, again, that they're Gaussian. We're going to assume that we don't know the parameter vectors, so we don't know the exact Gaussians that go into our density, and we don't know the actual category labels for the samples that we're going to be looking at. Okay. So we're going to start by modeling the observed density as a mixture of C different class densities. So in this case, we have a class density, or we have a sample density here, the probability of observing a feature vector given a set of parameters. And these parameters control just any sample that you might observe. So there's no class subscript here. This is just what's the probability of observing a particular feature vector. And what we assume is that that probability is given by a mixture of each class. So this cycles through all of the classes. This is the class conditional density of that feature vector. And this is the prior probability of that class. So this is essentially a mix of the densities for each class, and that mix goes into the density of all the samples. And here, this theta is essentially a set of all of the class parameters. So in this form, P of x given theta is known as a mixture density because it's a mix of all these class conditional probabilities. The conditional densities are the component densities, and the priors are the mixing parameters. So this is essentially a weighted sum of all of the individual densities for each class, and what we end up with is the data that we observe. So this is the probability of observing a particular set of sample. So here's what that looks like. Let's say we just started recording this feature x1. Doesn't matter what x1 actually is. Here is the domain of all the possible feature values. Here is the probability of observing feature values along this x-axis. And if we just start observing samples, not caring about what class they come from, we end up with a density that looks like this. Okay? And the assumption here is that we get this density because we're actually seeing a mixture of all the class-specific densities. If that's true, then our class densities might look something like this, where we have 3 Gaussians, each of which corresponds to a different class, and each of them is contributing to the overall observed density of the samples. Okay? And so each point here is a result of the green line plus the blue line, plus the red line. And it's the value of the density times the likelihood of observing that particular density. In this case, we're making an assumption that each density is equally likely, so it's just this density plus this density plus that density. And that's what gives us our black line. Okay? So here's that equation again. This is the summation. These are all the mixtures. And this is the observed density. Our unknown is the set of parameters here, so that's what we're trying to solve. Once we have the parameter sets, we can basically unmix the density and figure out which classes are the largest contributors at each point of x, and then classify the new points accordingly. Right? So the idea, if I could just go back a second, is to use this, figure out what component densities could have created this, and then classify new points based on which component density they belong to. Now, we may not know which component density belongs to which real class. So if these are, let's say, tumors, and we have blue is benign, green is indeterminate, and red is severe or malignant, we may not know that given just the densities. But we can basically estimate that there are 3 densities. We can say that here are the parameters of our densities, and then we can classify new samples belong in either class 1, class 2, or class 3, whatever those classes end up being. Okay? So that's the goal. One question we might have is, if we have an infinite number of samples and we know the underlying form, then is the theta unique? So in other words, are there different combinations of class densities that could give us the same observed set of samples? We call a density identifiable if that's true. So this is just a fancy way of saying, let me back up again. Is there only one way we could have gotten this black line? Or is there some other combination of these 3 densities that could also give us this black line? Right? A good example of this might be, let's see. Can I draw here? Yeah. So a good example of this is, let's say that you have an observed density like this. So this is P of x. Okay. This is x. Let's say that you know that you have 3 densities that make up this result. It's possible that there are multiple different ways in which you could observe this density given 3 components. For example, you could have 2 densities that have the same mean here, and then 1 density that looks like that. Right? So 1, 2, and 3. This is one possible way you could get this, or you could have your second and third density be over here. So you have 3, 2 here. I drew that a little bit weirdly. And then you have your big density over here. So 1, 2, and 3. So you could have something that looks like this, right? So you can get the same output density, but with different combinations of mixtures. So basically, a density is identifiable if there can only be one such combination of those mixtures. Okay. So we can use maximum likelihood estimation to figure out what these densities should be. So suppose our data set, suppose our density gives us a set of data, x1, x2, x3, and so on, and that makes up our training set. The likelihood of observing a specific density is essentially the joint density, which is the likelihood of observing a specific data set is the joint density P of our data set given theta is equal to the product of all the individual sample densities. Right? And we've seen this before. We've seen what's the chance of observing a particular D. It's the chance of observing this X multiplied by the probability of this X multiplied by the probability of that X, and so on until we get to the final X. So the likelihood of observing that D is equal to the product of all the individual X's. Okay. So if we're looking to find the parameter set which maximizes the likelihood that we've observed that particular training set, we have to essentially convert this to a log likelihood, take the derivative, set the derivative equal to 0, then solve for the parameter set. And that's going to give us our estimate of our parameters. Okay? So we can essentially represent this as ln of each of the individual densities. Right? And remember, eventually we're going to say this is a Gaussian, so that's why we take the log likelihood. If we want to calculate the derivative of this with respect to theta, we remember that this theta belongs to each individual class. So this P of x given theta is actually part of this. Right? So the derivative of theta with respect to the class of the log likelihood is equal to 1, this should be a fraction here, 1 over P of x given theta times the partial derivative of theta with respect to class, and then each of the individual mixture densities. If we introduce the posterior probability, we can write this in terms of the component densities. Okay, so again, this is using Bayes' rule to convert the probability of observing a particular class given a particular sample and r theta is equal to the probability of observing a sample given that we know what class it came from and what the parameters governing that class came from, multiplied by the probability of observing that class, divided by the overall sample density. So then we could write the previous derivative using this substitution. So we basically take this and use this term in our log likelihood over here. Okay. And so this is the summation of all the samples. This is the theta with respect to each class. And so this is what that looks like. So then we set this equal to 0, and we solve for the class-specific parameters theta sub I. Okay? So we'll show how to do that in a second. So let's say that we're just estimating the mean from our data set, and we're estimating the mean for each one of our mixtures. We've already assumed that we know the form of the densities, so that it's Gaussian. There are 4 parameters that we don't know. One is what the multivariate mean is, so we're going to call this bold mu sub I. So this is the multivariate mean for each one of the classes. The covariance matrix for each one of the classes, the prior probability for each one of the classes, and the total number of classes. Just like with linear discriminants, for simplicity, we could start by assuming that we know 3 of these. So we assume that we know the covariance. We can assume, for example, that the variance of each class is going to be equal to one another. We can assume that we know the prior probabilities. So we could say that they're non-informative, which means it's just the fraction of each class. And we're going to assume that we know the total number of classes that we're interested in, which is C. So then the goal is just to figure out what the multivariate mean is supposed to be. So now we have unknown mean vectors. So once again, we take the log likelihood and we take it of the Gaussian so that we can simplify a lot of things. So if this is the log likelihood of each sample, given the class and given our theta, which now is just mu because we assume that we know the covariance, we end up with this equation. And we've seen this equation before in previous lectures. When we take the log likelihood of a Gaussian, we end up with something that looks like this. We take the derivative of this with respect to mu. So the derivative of this probability with respect to mu, we could basically get rid of this because mu is not in there. And we end up with, this is essentially this squared times this. So this squared, when we take the derivative, the squared comes down, gets rid of this fraction, and so now we just end up with this times x minus mu. So we have this right here. And we drop it into the old MLE equation for finding theta, which is essentially this. So we set this equal to 0, and we solve for mu. So we set this equal to 0. If we multiply by the covariance and we move around some terms, we're left with mu is equal to a fraction defined by the density, the probability of the class given the sample, multiplied by the sample, divided by the summation of all the possible densities. In other words, mu hat is a weighted average of the samples. Okay? So that's essentially what this boils down to. The weight for each sample is an estimate of how likely it is that that sample belongs to the ith class. Okay? So the weights here, so if this is a weighted average of the samples, then the weight is an estimate of how likely it is that this sample belongs to that particular class. Right? Does this give us our mean? Unfortunately, you can't solve for this explicitly if you just have a set of samples with no classes. So what you can do is you can perform an iterative search. So you select an initial value for mu, an initial guess, and then essentially you update by using the previous estimate for mu, estimating the density, and then that gives you an estimate of the new weighted average of all the samples in that class. I'll show you an example of this in a second. This is essentially a gradient ascent method, which means that eventually we're going to converge to a point at which subsequent iterations of our guess for the mean value are approximately equal to the current guess, and then we could just stop. As with all iterative approaches, once the gradient is equal to 0, we're only ensured that we've reached a local maximum value. Right? Remember, we have to be careful about local versus global maxima. So let's say that we have a two-component, one-dimensional normal mixture. So let's say that we know that our density of samples is made up of two classes. If I were to draw this out, it might look something like and like that. Okay, so we have two densities here, and these are the samples that we've observed. And so we're going to assume that this is two components, which means there's two mixtures going into this. And we're going to assume that it's one-dimensional, which just means that we're just dealing with a single variable. And so we have this density here is our first component, and this density here is our second component. And what we'd like to do is estimate what these two parameters are. Okay? So we can pull a set of samples sequentially from this mixture, so we could start observing and recording our feature samples. And these samples are used to calculate the log likelihood function, L of theta, which is essentially mu1 and mu2, is equal to the sum of the log likelihood of each individual sample. So if we observe this set of samples from our two-component mixture, then we might have a source distribution that looks like this, right? Sort of like what I drew previously, but just reversed. Okay. So what we essentially start doing is we pick a random mu, and then we start iterating, and we basically start trying to estimate the likelihood that our estimates are the true means. And eventually we get to a point where the mean values, right, this is mean 1 and this is mean 2, we get to a point at which the mean estimates for density 1 and density 2 are no longer changing, which means that we're at this local maximum. We've maximized the likelihood of mu1 and mu2. Okay? So you can see that sample size becomes really important. It's important to have a significant number of samples to estimate your parameters. And what would it look like if we had insufficient samples for this problem? You've probably seen examples like this before. If you have 2 dimensions, you can build a scatter plot that looks kind of like this. Right? Now, if I were to ask how many samples or how many means do you think we have, let's say we know or we can estimate that we have 2, I might say, well, there's a mean here and there's a mean here, right? But then as we collect more samples, we start to see something emerge. We have some samples over here, samples over here, and samples over here. And then as we collect even more samples, we end up with a thicker cloud here, here, and here. As we collect more samples, the estimate of our means changes. Even if we start here and we assume that we know that there are 3 samples, where to put those means in this cluster is not obvious. And so we might end up with a sample point here and a sample point over here, and then those means get more refined as we iterate further through the data set. Okay. So let's continue, and let's say that now we want to estimate our covariance as well. So if we don't have any constraints on the covariance, then we have a problem. So one of the components to this is that we have to put some kind of constraints on our covariance measurement. So let's say that our 2-component mixture looks like this. Again, now we have not just our means, but we have our means and our standard deviations. And here, again, we have our component 1 and our component 2. Okay, and in this case, we have component 2 has a variance or a standard deviation of 1, and over here, our standard deviation is, we're not sure what it is. Okay, and over here, our mean is also 0. So then the mean is 0, the variance is 1, or the standard deviation is 1, and so this is our 2-component mixture. Okay, so let's set the mean of the first component to be a number, x1. So for the density of x1, or the probability of x1, given our parameters, the first term's exponential goes to 0, right? So the probability of x, if x is x1, so if x is at the mean, then this is exponential of 0. And so we end up with the probability of x1, given the mean and standard deviation, goes to 1 over 2 root 2 times sigma plus 1 over 2 root 2 exponential of the rest of this. Okay. For all the samples which are not the mean, the first term's exponential remains. So in that case, whatever the probability is, right? So let's go back to here. So if the sample that we're looking at, the probability of the sample we're looking at is equal to the mean, right, then this goes away, this goes to 0, which means all of this goes to 0, which means this goes to 1, which means we just have this term, right? That's what's down here. And this term just kind of stays there. But if that's not the case, then we can't simplify this. We can't simplify this down here. So the probability is now greater than or equal to that term on the right-hand side. So the probability, the joint probability for x1 through xn is the product of all of the above. So with some rearranging, we end up with the probability of each sample, or D, given the mean and standard deviation, is greater than or equal to 1 over sigma plus exponential of this term times 1 over 2 root 2 to the n times exponential of that summation, right? We're essentially multiplying many of these probabilities together. Right? So what we end up with is exploding equations with small variance, because the important term here is this guy right here. Right? So what happens is, if our standard deviation is really, really small, then this value gets really, really big. And if this value gets really, really big, then that means that this probability sort of explodes. Okay? Because this is always going to be greater than or equal to this, whereas if our variance is really small, then this becomes too big. So what that means is that the MLE solution is singular. And if you're running this in MATLAB, you may get some situations where it tells you that the solution that it finds is singular or poorly formed. So to get around this, we put some constraints on our sigma. Recall the likelihood equation when you're finding mu, right? Again, we replaced our probability with the Gaussian. We took the ln of the Gaussian and we ended up with this whole thing. And then we said, okay, we're going to take the derivative of this with respect to mu, which means this goes away, and blah, 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 right? But now we're not getting rid of this because we're not assuming, we have to find sigma as well as that. So just like before, we want to differentiate and set to 0, but this time we have to differentiate with respect to both mu and sigma. Okay, so now we have a two parameter problem that we're trying to solve. So remember the relation that we had previously, right? This was the relationship between the mixture densities and the sample-specific, or the class conditional probabilities for each sample. We took the derivative of this and set it equal to 0. If you sort of solve for each one of the parameter values, you end up with something that looks like this. So the prior for each class is equal to the average of the prior probability, or of the sample conditional probabilities for each class. The mu is again the weighted sample of each point. And the sigma, or the covariance, is basically a weighted covariance, or a weighted variance. This should actually be a capital T here. Yep. So what do these mean? So here we have the likelihood of a specific class, omega I, is the fraction of samples from omega I. Right? So this here is the average, or the fraction of the samples that belong to that class. Okay. Here, mu is the mean of the samples within that class. Right? So again, this is the probability of omega I, the mean of I, this is the probability associated with that class given the sample and the parameter set. So here you have the sample being multiplied by that. So if this probability is very low, then this does not contribute to the mean. If it's high, then this does contribute to the mean. And here we have the corresponding covariance matrix, which again has the same multiplication. So here is the covariance matrix associated with class I. Here is the probability of class I times the covariance of the samples at class I. If this probability is between 0 and 1, then all the samples play a role in the estimates, not just those belonging to omega I. Right? So if there's some chance that a sample belongs in multiple classes, then each of those classes is going to play a role in determining what the average value or average feature for that class is. Okay. One final point. So here, the probability of the class, given the sample and given theta, we've written this quite a lot. For each of the equations, we could basically substitute in Bayes for this probability. So the probability of the class, given the sample and the parameter set, we basically represent this using Bayes, which is right here. And remember that we're assuming that this is Gaussian. Here, let me get rid of some of these lines. We're assuming that this is Gaussian and this is Gaussian because these are the same thing. So we can replace these with Gaussians, which looks like this. Okay. So now this isn't very, very pretty, but what it is it means that we do have an explicit way to calculate each of the unknown parameters given our sample set. Right? And we could do this just based on the samples themselves. As long as we know how many classes there are, we can use this equation to solve for the parameter sets for each one of the classes, just given unlabeled samples. And again, we take an iterative approach to solving for each one of our classes. Okay. And again, we take an iterative approach to solving for each one of the parameter sets. So for mu as well as sigma, we're basically just taking the average of all the points with respect to each individual class. And this is done iteratively until this mu no longer changes. Okay. Okay, so let's talk a little bit about k-means clustering. So we have this big ugly equation right here. We have essentially replaced each one of the probabilities of our densities with Gaussians, and I've highlighted this region right here. So the value of the density is high if the Mahalanobis distance, or the distance between a sample and the mean, is small. Okay, so think about that. If this distance is small, then this becomes small, which means this becomes high, right? Which means the entire term becomes high. And that makes the probability of that class to be high. So intuitively, this means that if a sample is close to the centroid of a class cluster, then the likelihood of it belonging to the associated class is also very high. So if we replace the Mahalanobis with the squared Euclidean distance, we can find the mean nearest to each sample. So then we can approximate the probability of a class like this. We could say that the probability of a class, given that we have a particular feature and given the set of parameters for our mixture, is either 1 if I is equal to m, or 0 otherwise. Right? So in other words, if I of this class is equal to m, which is the mean closest to x, then the probability that x belongs to that class is 1, and it's 0 otherwise. So then we can plug this into the equation we got before and solve for each one of our means. We initialize by selecting C class centroids at random from the unlabeled data, and then we iterate. So each time you iterate, you're changing your class means, or your cluster means rather, and your estimate of which samples belong to which cluster. Okay, so this is the algorithm for k-means clustering. You start off with a random estimate of your mean. Right, this is the mean space here, mean mu2 and mu1. So this is your parameter space. You start off at a random location, and then you iteratively update so that you approach the true mean value. And no matter where you start, if you go down the gradient, right, of your samples, or of your likelihood space, then you will end up at the same location, unless you hit something weird like a saddle point, which again, you need to be careful of local minima and local maxima. So maximum likelihood estimation and k-means are very similar to one another. Since the overlap between the components is relatively small, so in other words, these densities are pretty far apart from each other, we arrive at basically the same answers for each of the mean estimates for class 1 and class 2, or for component 1 and 2. Okay. So here's how this looks. Let's say you have a cloud of points, which is given by these black dots, and you pick 3 random dots to serve as the means for your samples. Okay. And so what these black dots do is basically divide up the space, like so, on iteration 1. So then what you do is you calculate what the new mean value is for all the points that belong to cluster 1, all the points that belong to cluster 2, and all the points that belong to cluster 3. And you can see that the mean value of this cluster is not over here, it's actually closer to this. So we move the mean value closer to this, and then we recalculate this, right? This cluster centroid moves over here, this one maybe moves this way a little bit, right? So now we end up with our second iteration. So now again, we have our new estimate for our means. We assign points to the cluster associated with the closest mean value. And then we say, okay, now let's find the new mean value within this cluster. And the new mean value for this cluster might be over here. And the new mean value for this cluster might be over here. Okay. So then on the third iteration, we end up with something that looks more reasonable. And again, this goes back to the k-means algorithm, where you're basically going to do this until you don't change where the mean value goes anymore, which means these lines basically stay the same. And you've reached convergence. Yeah. So k-means is a staple of unsupervised clustering methods. It's very commonly used. It's pretty simple. It's relatively fast. When you calculate the total amount of time or the order complexity of the algorithm, it's pretty fast. It's basically just the number of patterns, the number of features, the number of clusters, and the number of iterations determines the runtime. And it typically finishes pretty quickly, assuming that you have good clusters that are pretty well separated. It fails in a couple different situations, right? So if we're wrong about the number of classes, we're essentially going to converge on two means that don't mean anything. So let's say that instead of 3, we say that we need 2 classes, or instead of 2 classes, we say that we need 5 classes. It's actually going to give us 5 clusters, but it might not mean anything when we look at it. If the clusters are too close to one another, then there may not be enough samples to properly ascend to the true value of the mean value. So if you have two, let me just draw this out. Let's say that your observed density looks like this, because cluster 1 is like this, and cluster 2 is like this. You may not have enough samples to actually figure out the difference between these two means. Okay? And if that's the case, then you're going to have a hard time arriving at mu1 and mu2 using that method. Remember that everything is dependent on your features. So if that's the case, if you're having a hard time converging, it's possible that you're looking at a bad feature set or a bad set of features for your chosen classes. Okay, let's talk about evaluation. So far, we've been talking about clusters and classes as being synonymous, but we know that that's not the case, right? In the case of unsupervised classification, you don't know which classes are associated with each sample. And so you can't really say that this is a malignant cluster and that's a benign cluster unless you know something about those data labels. An underlying density with multiple modes could represent the same class, while a unimodal density may represent multiple classes, which would mean that it's a bad feature to use for discrimination. We make a lot of assumptions about the form of the data, but clearly we could estimate perfectly valid parameter sets and completely miss the underlying structure of the data. Okay? Here's a good example of that. So each of these clusters has exactly the same mean and standard deviation. And it's designed to illustrate the fact that you can't rely on the parameters to actually define your clustering. So the question that we come up with is, how do we know if we've got a good cluster? Okay, and that's what we're interested in. So if we're interested in finding subclasses in the unlabeled data, we have to define what we mean by subclasses. We could say that we just want to find clusters, but how do you define what a cluster is, right? In some cases, it can be very difficult. As I showed previously, if you don't have enough samples, then you're going to end up with a cluster that doesn't really look good. We need a way to say that samples in one cluster are more similar to each other than they are to samples in another cluster. Okay? And we also need a way to evaluate a given partitioning of the data set to say that clustering result A is better or worse than clustering result B. And this can be surprisingly difficult when you start looking at a lot of data sets. But we can start by using a distance metric to define the clusters in the first place. So let's say that we have a data set like this, where we have a set of samples in two-dimensional space, right? So x1, x2, and we set a threshold for whether or not samples should belong to the same cluster. Okay? And in this case, the threshold is too high, right? Because every point is connected to every other point, so we end up with one big cluster. So what that means is essentially that the distance metric, or the distance threshold that we set, is too high. So we can reduce it a little bit, and we can end up with these kinds of clusters here. So now we have a data set where all these points are closer to each other than they are to any other points. All these points and all these points. But you end up with these kind of orphan clusters here, right? These might be outliers, or they might represent just one or two samples from very rare clusters that are actually dissimilar from this one and from this one. Right? If you set your distance threshold too low, obviously you get this sort of solution where only points that are right on top of each other belong to the same cluster. So this is clearly not correct. So the question is, how do you decide what cluster arrangement is actually the right one? So generally speaking, we assume that the correct distance metric is Euclidean, which means that the shortest distance between 2 points is a straight line. So we assume that the feature space is Euclidean, a Euclidean space. This is justified if the space is isotropic, which means that distances in one dimension are equivalent to those in another, which you can ensure through things like data normalization, and that the data is evenly spread, so that the samples in one part of the feature space, the distance between them is just as significant as the distance between samples in other parts of the feature space. The Euclidean distance is robust to rigid transformations of the feature space, like rotation and translation, which is good, but it's not robust to arbitrary linear transformations, which can distort distance relationships. Right? And this figure from the book kind of illustrates that. So in this case, you have linear transformations of each feature separately using a distance metric to define your clusters, and you end up with two very different clusterings from one another and very different from the original feature space. So when you're defining your cluster memberships using distance, you have to make sure that the features are scaled the same way. You can try to counteract this through normalization, where you translate and scale the data to have zero, mean, and unit variance. And you can also rotate the coordinate space so that the axes coincide with the eigenvectors of the covariance matrix. And this is a part of principal component analysis, which we're going to cover in a little bit. But normalization obviously has its own problems. So you can sometimes normalize in such a way that you end up reducing the amount of separation between your two clusters. We'll talk about this more in subsequent lectures, this idea of normalization and looking for areas of maximum variance to project your data onto, but it's something to be aware of when you're evaluating your clusters. Okay, so to conclude, will supervised methods always outperform unsupervised methods? It depends. Having more information like labels is better, but you run into the risk of overfitting. You can run into the risk of bias by saying, I know that there are only 2 classes in this data set, or I know that there should be 5 classes in this data set, but the data itself doesn't support that hypothesis. Overfitting isn't just fine-tuning your decision hyperplanes, it's also when you make assumptions about the data set, like picking the number of classes or picking too many mixtures for your densities that are not correct. So overfitting could be that you're coming into the data set analysis with some kind of bias that's driven by your supervised labels. Sometimes clustering can give you insight above and beyond what you thought you knew about a particular data set. So if you think you have 2 classes and you find 3 clusters, that could be very useful to tell you that the problem is actually more complex than you thought it was. If you thought you had 5 classes and you only find 2 clusters, that probably means that the features that you've selected for discriminating your 5 classes are not robust enough or not specific enough to capture the different classes. But it could mean that these 2 clusters represent sort of groups, natural groupings of the data that you might be interested in. So that is also important to know. So in the next lecture, we're essentially going to start talking about how to evaluate and how we choose our similarity metrics and our distance functions. In the literature, Euclidean distance metric is usually assumed. So if you're trying to figure out cluster distances, you typically go with the Euclidean distance. But with nonlinear data sets, this may not be true. And that's what we'll talk about in the next class. We're also going to look at how to evaluate our clusters by calculating different criterion functions. So how do we know that one cluster is actually better than another, or one set of cluster memberships is more accurate than another? We're going to do that by defining certain criterion functions and talking about them in the context of different clusterings. And we may not look at all these, but that's the goal. And I'll try and show some examples of this in the code. Okay? So let me know, leave some feedback if this recording is useful. If you think that it is not working or you find it confusing, I can try and slow down. I can try and change the way I make my recordings. But please be specific. Don't just say that it's terrible, because that doesn't really help me. So I'm trying to, I'm hoping to improve the quality of the presentations. So if you have any suggestions on how to do that or any difficulties, please let me know. All right. Thank you. Have a good day.